In this lecture, we're going to discuss the surface charge that's associated with the polarization. Let's start by reminding ourselves of a couple of concepts that we've seen already. The first is that a bulk polarization which we call P, has units of electric dipole per unit volume. And electric dipole, of course, has units of charge times distance. So this is equivalent to charge per unit area. And so we associate, just on a dimensional analysis, a surface charge with a bulk polarization. And in particular, if the surface is perpendicular to the direction of the polarization, like the example we've shown here, then if the bulk polarization has value P microcoulombs per square centimeter, say, the size of the surface charge is P microcoulombs in every square centimeter. And it'll be negative at the negative end of the polarization, the negative end of the dipole, and positive at the positive end. In general, if the surface is not perpendicular to the polarization, then the surface charge is given by this bulk polarization, which is a vector, the dot product of the bulk polarization with the surface normal. So N here is the unit surface normal. Second point to remind ourselves of is the multi-valuedness of the polarization. So the polarization for a bulk periodic solid is uniquely defined, but it's a multi-valued quantity. We call it the polarization lattice. So we can write it as some P0, say, plus N times PQ, where PQ is the electronic charge times any lattice vector divided by the unit cell volume, and we call PQ the polarization quantum. So just reminding ourselves of these two facts that we've covered already raises the question, when we want to calculate the surface charge associated with some particular surface, what should we choose for P bulk? We know that the polarization is a multi-valued quantity, and so it's not immediately obvious which of these multiple values we should choose to calculate the surface charge. So it turns out there's a recipe for how to determine the bulk polarization that you need to use to work out the charge on a particular surface. And the recipe is to take the unit cell that tiles the semi-infinite plane that contains your surface. So you need to look and see which unit cell, periodically repeated, will make a system that's periodic in both directions parallel to the surface and beneath this and continuous beneath the surface and reproduces the surface plane. We'll look at some examples at the moment, in just a moment. So that's the first thing. And then you calculate the dipole moment per unit volume for this choice of unit cell. And this is the appropriate value for P bulk. So let's look at an example of the 001 surface of barium titanate. So barium titanate, we know, has the perovskite structure. In which we have barium ions at the corners of the unit cells, oxygen ions at the centers of the faces, and the titanium ion in the center of the unit cell. And I'm going to simplify this structure by just sketching a cross-section of the ions in each plane. So let's just sketch a cross-section of the ions in each plane. And then in each unit cell, I have in the bottom plane barium and oxygen, and halfway up the unit cell, I have a titanium and 2 oxygens, and then at the top of the unit cell, I have barium and oxygen again, and so on. And this is periodically repeated. And of course, it's periodically repeated also in the X and Y directions and out of the plane and into the plane. And strictly the unit cell that I've sketched here is the high symmetry. It's the paraelectric phase. In the ferroelectric structure, the ions are a little bit shuffled away from these perfect straight lines, but still broadly, this is the structure of the layers. One important point to note is that the barium ions are divalent, and the titanium ions have charge 4+, and the oxygen ions have charge, each have charge 2-. So these layers have charge of 0. Okay, so let's apply our recipe. And I'm going to go to another page because I want to have space to do first the paraelectric structure. Centrosymmetric, high temperature paraelectric structure. And then we'll compare it to the ferroelectric structure. And let's start with a flat TiO2 surface. So my structure in this simple sketch has TiO2 on the surface, and below it, barium oxide, TiO2, alternating infinitely, and to the left and right, and out of the plane and into the plane. It's also periodically repeated, and our surface is above the TiO2. And so following my recipe, I have to choose a unit cell, which I can repeat periodically to create this semi-infinite plane of barium titanate. And the choice here is obvious. My unit cell is going to look like this in my two-dimensional cross-section sketch, because then I can repeat it periodically and build up this half plane of barium titanate. So let's calculate the dipole of this unit cell. And in the Z direction, let's label this direction Z, and I'm going to make the position of the barium oxide, Bz is equal to 0, and then my dipole in the Z direction is the sum over the ions, over the layers, sorry, of the charge on each layer times the position in the Z direction of the layer. I'm combining all of the ions in each layer into one common charge. And this is trivial because the charge on each layer is 0. So in this case, I get 0 times 0 for the first layer, plus 0 times half a unit cell for the second layer, which is trivially 0. Let's make the size of the unit cell be A. So my dipole per unit volume, which is P bulk, is 0 divided by the volume, which is 0. So this is what I would expect for the paraelectric structure of barium titanate. The polarization of the unit cell with a flat TiO2 surface is 0, and there's no surface charge. Now let's look at the ferroelectric structure. And we know that for a ferroelectric, the polarization of the ferroelectric structure is going to be whatever the polarization is for the paraelectric structure, plus what we call the spontaneous polarization, where the spontaneous polarization is 1 over the volume times the sum over the ions of the charges on the ions times their displacement from the paraelectric to the ferroelectric structure. So delta Z here is the distance that the ions move along the Z-axis from the paraelectric to the ferroelectric structure. So the spontaneous polarization here is the change in polarization between the ferroelectric and the paraelectric structures. And we've just shown that for the flat TiO2 surface, the bulk polarization in the paraelectric case is 0, then we can just write down by inspection, without making a separate calculation, that the bulk polarization in the ferroelectric structure is equal to the spontaneous polarization. And so the charge per unit area for the flat TiO2 001 surface of barium titanate is just equal to the spontaneous ferroelectric polarization in the 001 direction. And of course, this surface charge is electrostatically unfavorable. And there's a problem for ferroelectric thin films. So we have a very thin film of a ferroelectric, such as barium titanate. The polarization perpendicular to the direction of the film, the surface charge can be large and electrostatically unfavorable. And so one either needs metallic electrodes to screen to compensate the surface charge, or, and even in the presence of metallic electrodes, the polarization can be suppressed. It can rotate into the plane, or even sometimes a paraelectric phase can be more stable. So that seems kind of trivial, and you might wonder, well, why did we worry about the multi-valuedness of the polarization, or where would that come in? So let's take a look at a 001 surface. It's not smooth. It's flat, but it's not smooth. And again, we'll first look at the paraelectric case. And what I mean by that, I'm going to take a surface that looks like this. So I have a barium, and then TiO2, and then barium oxide, TiO2, and so on. And then my next unit cell to the left would then have another TiO2 and a barium. I'm going to draw two of them just so it's clear in this case. So I still have a flat 001 surface, but it's not smooth. It has these missing oxygen atoms. So now let's follow the recipe again and choose the unit cell that will tile this lower semi-infinite half plane. And again, I can do that by inspection. The unit cell has to have the stoichiometry of the bulk if it's going to build up the bulk. And you can see by inspection, it's going to look like this. I can periodically repeat this unit cell. Let's do it again here. And down here, I'll capture so this oxygen that I haven't drawn, put it in, and build up the entire semi-infinite plane of barium titanate. So we can follow our recipe and work out the bulk polarization for the paraelectric structure as the dipole, the unit volume of this unit cell. Let's take Z is equal to 0 to be at the oxygen, which of course has a charge of 2 minus. And so my bulk polarization is then charge of -2 from the oxygen times 0 for position Z is equal to 0, plus a charge of 0 for the TiO2 layer, which has 0 charge, times A/2 for the position of the TiO2 layer, plus a charge of +2 for the barium, times position A, where A is the size of the conventional unit cell. It's the barium-barium space. And these are all, of course, times the electronic charge. So this, if I then gather my terms together, is +2 times the electronic charge times the unit cell length divided by V, which is +2 times the polarization quantum. So we see that in this case, the surface is charged even in the paraelectric structure, and so it's not electrostatically favorable. If we were to look at the ferroelectric case now, then just as before, the bulk polarization for the ferroelectric case is this +2 polarization quanta plus the spontaneous polarization that arises in the transition from the paraelectric to the ferroelectric structure. And we can see here, of course, the spontaneous polarization can have either positive or negative sign, depending whether the polarization is in the up direction or in the down direction. And so it can either increase or decrease the surface charge. Now, this particular example is not the most relevant because the surface is unlikely to be stable in barium titanate, but this concept is going to become important in what we'll discuss next. Okay, so our next example then, I want to look at the case of bismuth ferrite. Which is a popular material because it's multi-ferroic. It's both ferroelectric and magnetic because of the presence of the ion. And the multiferroism is not going to interest us for now, but what is interesting is that in bismuth ferrite, the A site cation and the B site cation are both trivalent. They're both +3 cations, and the oxygen, of course, is again -2. Which is different from barium titanate, where we had barium 2+ and titanium 4+. And the paraelectric case is then just like the example of lanthanum aluminate that we looked at earlier, which is a centrosymmetric perovskite with both cations having charge +3. We call it a 3-3 perovskite. So let's look at the two obvious cases of a smooth, flat bismuth oxygen surface and a smooth, flat FeO2 surface. So in the case of the bismuth oxygen surface, then our unit cell that will tile the semi-infinite half plane looks like this. And in the FeO2 surface, the unit cell with the opposite way around. And so again, our structure periodically repeats. In the XY plane and goes infinitely down to minus Z. And let's work out the polarization in both cases. The charges on the layers are charge -1 on the FeO2 layer and charge +1 on the bismuth oxygen layer. And let's put, again, Z is equal to 0 at the level of the lower layer in the unit cell. So then the polarization for the unit cell with the bismuth oxygen surface is 1/V, 0 times -1 for the FeO2 layer, plus A/2 times +1 for the bismuth oxygen layer, times the electronic charge, which is equal to E/2 times A/V, which is plus a half polarization quantum. We make the same calculation for the FeO2 surface. Then the polarization is 1/V, 0 times +1 for the bismuth oxygen layer, plus A/2 times -1 for the FeO2 layer, times the electronic charge, which is minus E/2 times A/V, which is minus a half polarization quantum. So now the two obvious choices of surface for bismuth ferrite have opposite charges, equal and opposite electronic charges. And again, if we see that both of these fall on a centrosymmetric polarization lattice, which is allowed to have values of the half quantum plus or minus n times the polarization quantum. And to get other values, we would have to create non-smooth flat surfaces. Then we would get answers, for example, like plus 3/2 times the polarization quantum and so on. It's particularly interesting if we actually put in numbers for bismuth ferrite. If we look up what the size of the lattice constant is and what the unicellular volume is, and put in numbers, what we get for the bismuth oxygen surface for plus the polarization quantum over 2, the value is plus 50 microcoulombs per square centimeter. And the value for the FeO2 surface is obviously minus the same amount. And this is interesting because completely by coincidence, the value of the spontaneous polarization, the size of the spontaneous polarization in the 0,0,1 direction in bismuth ferrite is 50 microcoulombs per square centimeter. And remember, the bulk polarization for the ferroelectric is equal to the bulk polarization for the paraelectric case plus the spontaneous polarization. And so depending on the sign of the polarization and the choice of bismuth ferrite surface, one can have the spontaneous polarization from the ferroelectricity exactly cancelling the polarization from the paraelectric half quantum. So the spontaneous polarization from the ferroelectric displacements, can exactly cancel the polarization from the half quantum for two combinations of surface choice and polarization direction. So for the correct combinations of surface termination and polarization direction. So let's just write down what those are. And here's a sketch. So here's the structure of bismuth ferrite. In practice, in addition to the ferroelectric distortion, there are also rotations of the oxygen octahedra, which are shown here. But you see very clearly the bismuth oxygen layers and the FeO2 layers. And in the paraelectric state, with the FeO2 minus surface, then the polarization is minus -50 microcoulombs per square centimeter, whereas on the bismuth oxygen surface, it's plus 50 microcoulombs per square centimeter. So if my polarization is oriented from the bismuth oxygen surface to the iron oxygen surface, then the 50 microcoulombs per square centimeter of polarization from the ferroelectric spontaneous polarization exactly compensates that from the paraelectric half quantum. And so we call this a happy surfaces. In the opposite case, sketched here, the polarization is still oriented in the up direction. So the negative end is at the bottom and the positive end is at the top. And the spontaneous polarization still has the value of 50 microcoulombs per square centimeter. But in this case, it's adding to the polarization from the half quantum. And so the surface charge on the FeO2 surface is now minus 100 microcoulombs per square centimeter. And on the bismuth oxygen surface, it's plus 100 microcoulombs per square centimeter. So the ferroelectric polarization in this unhappy situation combine to make the surfaces doubly electrostatically unstable. Okay, so let's make a summary. Of what we've discussed this lecture. So the first is that a material with a bulk polarization has a surface charge given by the dot product of the bulk polarization with the surface normal. And this bulk polarization can come from spontaneous polarization in a ferroelectric. It can come from a half polarization quantum in a paraelectric, or a combination of the two. The second point is that in general, the polarization is multi-valued. And different choices of surfaces select different values of the bulk polarization lattice. And we looked at a recipe for how to determine P bulk for a general periodic solid. We saw that centrosymmetric systems can have non-zero values of P bulk, and as a result, non-zero surface charge. And we looked earlier at the example of lanthanum aluminate. This time we looked at paraelectric bismuth ferrite, and also bumpy barium titanate, where our P bulk is an integer number of polarization quanta. And in the example of bismuth ferrite, we saw that the spontaneous polarization can add to or subtract from the polarization from the ionic layer charges. We looked at the example of the spontaneous polarization of bismuth ferrite having the same size as the half polarization quantum of the paraelectric structure. So I hope these examples have convinced you then that the multi-valuedness of the polarization is really important at the surfaces of materials, of bulk periodic solids, and also at the interfaces between two materials. If we neglect to select the correct value of polarization when we think about the surface charge, then we'll get really physically meaningless results when we try to describe surface and interface properties. So that's all for today, and thanks for listening.